Hello everyone, welcome to the video. Today we are going to solve the problem longest common substring. In this problem, we are given two strings and we have to return the substring which is common to both the strings and whose length is longest. We have to return the length of such substring. We are going to solve this problem today. We will go through the thinking process, write the algorithm, and then also see a working code for the same algorithm. Later, we will also see how to return the actual longest common substring and not just its length. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note the key things given in the question. We are given that there are two strings and we have to return the length of the longest common substring. What does that mean? Now we know what is a substring. Substring means a contiguous part of a string. So it has to be a substring. Then it has to be a common substring. That means this substring should be present in both the strings given. And then it has to be the longest as well. That means out of all the common substrings that are present in both the string, we have to return the longest one and we have to return the length for it. So let us consider this example. We are given two strings A, B, C, D, G, H and A, C, D, G, H, R. In this string, the C, D, G, H, this substring is common to both the strings and this is the longest common substring here. So our answer that we will return is 4. So if we consider our solution as a black box, we are getting two strings as input and we are returning a length as output. One thing that we may have to note here is that it is possible that in the two strings given, there is not even a single character common. In that case, we should clarify with the interviewer that what should we return in such a case. The interviewer may say that in such a case you can return -1 or something like this. So based on this now black box representation of our problem, what will our function signature look like? Our function signature will look something like this. Let's start solving the problem. Now our aim is to find the substring which is common to both the strings and whose length is the longest. So what is the simplest approach that comes to our mind? We can first find all substrings in S1. We can represent them as just set of string. Now we need to shortlist among them only those substrings which are common to both. So we iterate through all of these substrings. In every iteration, we have the substring under consideration. For that substring, we will check if that substring is also present in S2. If it is, then our common check is passed. Now only thing remaining is that we have to track which one is the longest. Now since we have the substring, we know its length. Now to track the longest, we will need another variable whose purpose will be to track the longest substring seen so far. So if this length is greater than the max length seen so far, then we will update this variable. Once we are done with all the iterations, we can simply return the max length so far. And this will be the length of the longest common substring between the two strings. Now, our problem is how do we find all substrings in a string? This is a very common subproblem. We can simply use two pointers I and j to find all substrings. What will I track? I will track the starting position of that substring. And what will j track? J will track the end position of that substring. Since I will track the starting position, I can range from 0 till the length of the whole string. And j will range from I till the end of the string. So using these two nested loops, we can find all substrings in S1. Then our problem remains how to check presence of a string in another string. For this, we will mostly have built-in functions in whatever language we are coding. So with this algorithm, we are able to find the length of the longest common substring. Now let us try to understand what will be the time and space complexity for this algorithm. Let us say that the length of the two strings are m and n. then how much time will the first step take, finding all substrings in S1? It will take of the order of m square. Then how much time will this iteration take? This will also take the order of m square, this whole loop, because there are order of m square substrings in total. Now, coming to every single iteration, how much time will this check presence in S2? This has a built-in function, but it takes the time of order of n, the length of the string S2. Keeping track of max length so far is just a matter of updating a variable based on a check, so this will take order of 1. Therefore, the total time complexity of this algorithm comes down to order of m square multiplied by order of n. And what will be the space complexity? The space complexity will also be order of m square, because we will have to store these substrings somewhere in a set. So this completes the simplest approach that we had for our problem. But this is expensive, so let's see if we can do anything better. Since we can't think of any other straightforward approach, let us try to solve this problem using recursion. What does that mean? That means we have to identify just next smaller problems, and then we have to see if we can use the answers of those smaller problems to derive answer for our original problem. Which means that if somebody magically comes and gives us the answers to smaller problems, can we get the answer for larger problem using that? So how do we know what is our smaller problem? How do we go to the smaller problem? Now in this case, we have two inputs, the two strings. So what will smaller problem mean? It would mean that the size of at least one of the strings is getting reduced. So let's see what happens when we try to reduce our problem or when we try to go to smaller problem. Let's say that this encircled part is our smaller problem. Here we have reduced our first string by length 1. For the first string, we are only considering the string A, B, C, D, G. We don't consider the H character. Now, let us say somebody comes and gives us the answer to this encircled problem, which is M. Now, can we use this M and this H, that will be the new character added, to derive the answer for our original problem? Let's see. Here, M is equal to 3 because of CDG, which is the longest common substring in the two strings ABCDG and ACDGHR. Now, when we add H more to the first string, can we use this M and H to figure out what will be the answer for the overall? We can't really say that. With H, ideally the answer should become 4, but only this new character and the value of M is not sufficient to derive that. That means this simple recursion is not very straightforward. Therefore, we will have to think of something else. Let us make a few observations. Here, whatever is the substring that we are looking for will have to end at some or the other index in the original string. For example, here in S1, the substring CDGH ends at index 5. Now what can we say about this substring CDGH if we consider characters only till here? I mean, even if the characters were there beyond H, we don't consider them, we only consider the characters till here, then what can we say about CDGH for this whole string? We can say that CDGH is also a suffix of this whole string. Similarly, if we come to string 2, in second string S2, CDGH ends at index j is equal to 4. Now, if we only consider characters till this index, till j is equal to 4, and we don't consider r, that means the string in consideration is ACDGH. Now, in this string, what can we say about CDGH? CDGH is a suffix of this string. Now, what more can we say when we see these two here? We can say that CDGH is not just suffix for both of these strings. It is also a common suffix for both of these strings. it is also the longest common suffix for both of these strings if we consider the characters till I and the characters till j in S1 and S2. That means the longest common substring that we are looking for is one of the longest common suffix that can be found for a combination of I and j. What does I denote? What does j denote? These denote the characters, first few characters that we are considering for the two strings. Therefore, we have one more way of solving our problem. For every pair of I and j, we can iterate, and in every iteration, we can figure out the longest common suffix for that pair of I and j. What does that mean? That means we are considering for string S1 characters from index 0 till index I, and we are considering for string S2 characters from index 0 till index j. Now, in such two strings, what is the longest common suffix? We can get that, and then this will denote one of the common substrings between S1 and S2. Now we are concerned with the longest one, so we will need to track the length of the longest common suffix seen so far. We can track this in a variable max length so far, and whenever its length is greater than this, we will update its value. Finally, when we are done with all the iterations, we will return max length so far. Now this algorithm therefore will be able to return what is the length of the longest common substring. What do we mean by all I and j here? Here I can range from 0 till end index of S1 and j can also range from 0 till end index of S2. Now our problem becomes, how do we compute the longest common suffix for a pair of I and j? Let us take an example. Here we are considering I is equal to 4 and j is equal to 3. That means from the string S1 we are considering characters only till I is equal to 4, and for the string S2 we are considering characters only till j is equal to 3. Now if somebody asks us to calculate the longest common suffix between these two strings, what is the simplest thing that comes to our mind? The simplest thing that comes to our mind is that we can start two pointers. One points till the end of the first string and second points to the end of the second string. Now if the two characters are same, they form the part of the longest common suffix. If they are same, then we can advance both of these pointers to one point prior. We will again compare the two characters, and if the two characters are same, then we will again move both the pointers one position prior. Till when we will continue this? We will continue this till the two characters don't become equal or we have reached the end of one string. What will be the time complexity of such an approach? It will be order of n, where n is the length of the smaller string, because at worst case we may have to travel one string completely. Now this method is good if we have to calculate the longest common suffix between just one pair of strings. But we don't have to do that only for one pair. We have to do it for all I and j. In such a case, this method will be inefficient. How? Suppose we were dealing with a problem where both these strings also had h at the end of them. That means we were dealing with I is equal to 5 and j is equal to 4. Now again, if we have to compute the longest common suffix, how will we do it? If we go by the old way, we will have the two pointers at h and h in both the strings. We will compare the two characters and then move one position prior. We will continue to do that till we find a non-matching character. But isn't this inefficient? We already know the answer to this problem till I is equal to 4 and till j is equal to 3. The answer is m is equal to 3 because CDG is the longest common suffix between the two. Now, if we have added one new character to both the strings, we shouldn't need to calculate the longest common suffix again. We can simply make use of this answer and the new character. If the two characters are same, then our answer will be simply 3 plus 1 equal to 4. Have we just expressed our problem in terms of answers to smaller problem? We can say that longest common suffix for I, j will be equal to longest common suffix for I minus 1, j minus 1 plus 1 if the last characters at both the strings are equal. And what happens if they are not equal? Let's say here instead of h in S2 it was some other character like r. Then what will be the length of the longest common suffix? It will simply be 0 because even the last character is not equal. So this is our recursive relation to calculate longest common suffix. And if we know how to calculate longest common suffix, then we can very easily calculate the length of the longest common substring. So let us try to use this recursive relation to convert into algorithm so that we can compute longest common suffix. So this is the recursive relation that we identified in the last slide. Now, as with any recursion problem, we will go through this step by step. We have already done the first two steps. We have identified the recursive relation and we have also identified the inputs that will go into the recursive method call. What are those inputs? The inputs are I and j as per this recursive relation. But obviously I and j independently do not make sense since they refer to the characters in string S1 and S2. Therefore, we will pass S1 and S2 as well. Our main method will call this recursive method for all pair of I and j. We will get the answer for that I and j, and then we will here keep track of the maximum length, maximum answer that we have seen so far. And then finally we will return the maximum length seen so far. However, there is a very small complication here. What is the range of I and j? I and j both denote indices in the string. So they can range from 0 till m-1 or till n-1. So what will I equal to 0 and j equal to 0 refer to? I equal to 0 and j equal to 0 will refer to the first characters of both the strings. So when we say that longest common suffix for I, j where I and j are both zeros, that means we are taking into consideration only the first characters of both the strings and then trying to calculate the longest common suffix. But here we won't be able to consider the case where one of the strings is empty. For that we will have to handle things separately. So let's make a very small change here. So when we say that longest common suffix for I, j, let us say that this expression means that we are considering the first I characters of S1 and first j characters of S2. Note that it is different than what we have been considering so far. Here in the first string I is equal to 5 because it is at the fifth index at which this string is ending. But we are considering the 6 characters, total characters 6. Similarly here j is equal to 4. That means it is at the index of 0, 1, 2, 3, 4 where the string is ending. But we are considering 5 characters. So when we talk in terms of this recursive relation, here I and j will denote the first characters, first I characters or first j characters. Now when we say I equal to 0, that would mean first 0 characters. That means no character. Therefore, we will not have to consider the empty string case in a different manner. We can simply use the same recursive relation to handle the empty string case in this manner. But when we say that longest common suffix for first I characters and first j characters, then if we have to check the last character, it won't be denoted by I and j. For example, here we are considering first 6 characters, but the last character is denoted by index 5. Here we are considering first 5 characters, but the last character is being denoted by index 4. Therefore, in this recursive relation, we will make a small change that when we check the two last characters to be equal, we will check by s1 i-1 and s2 j-1. So this is what our recursive relation now looks like. What does it say? It says that longest common suffix of the two strings, if we are considering first I characters and first j characters of s1 and s2, what will it be equal to? It will be equal to longest common suffix of the two strings if we consider first I-1 characters for s1 and first j-1 characters for s2 plus 1 if the last characters are equal. And we know the last characters will be s1 I-1 and s2 j-1. Therefore, this recursive method here is returning the length of the longest common suffix if we are considering first I characters of s1 and first j characters of s2. Therefore, range here for I can be from I equal to 0 till n. What does that mean? We are considering first 0 characters and we are considering all n characters, which is s1. Similarly, j can also range from j equal to 0 till j equal to m. That means we are considering first 0 characters and first m characters, that is whole string s2. Now let us try to use this recursive relation to fill out our algorithm. So first of all, we check if the last characters are equal. If the last characters are equal, then we calculate the answer for our subproblem by calling the same recursive method for I-1 and j-1. And our answer here for I and j becomes subproblem answer plus 1. And if the two characters were not equal, then our answer is simply 0. Finally, we will return whatever is our answer. Now this, we have coded our recursive relation into our algorithm. But is this complete? No, it is not complete. Why? Because this will go into infinite recursion as the same method keeps calling on itself. So we need something called as base or terminating condition. And when does the base or terminating condition arise? It is usually reached when our input is the smallest. What is our input here? The length of the two strings that we are considering. So if we had I equal to 0 or j equal to 0, it would mean that we are considering first 0 characters of s1 or first 0 characters of s2. That means either of the two strings are empty. And if either of the two strings are empty, then what is the length of the longest common suffix? It is obviously 0. So we add this base condition. Now this algorithm is complete, but it has very high time complexity. Why? Because there are many overlapping problems. How can we say that? Let us say in our example, we started to solve for 5, 4. What does that mean? That means we are considering both the strings which are ending at g. Then here, since the two characters g at the end of the two strings are equal, therefore we will have to calculate for longest common suffix for 4, 3 as per this recursive relation. But since we are already in a loop calling for all I and j, therefore we will be calling for longest common suffix 4, 3 separately as well. Now this is a duplicate calculation of the same problem. This is inefficient. We should not do that. So how can we solve this? We can do one thing, that whenever we encounter an input for the first time, we calculate it and we store its results somewhere. And then whenever we encounter the same input again, we don't calculate for it again. Instead, we go into our storage and get the result for that input and directly return. If we can do that, we will eliminate the problem of duplicate calculation. How can we do that? We need to store this information that for a pair of I and j, this is our answer. What is the best data structure that suits this use case? We can use map, because in a map we can query by key and get the value in constant time, big O of 1 time. But with map we also have to define the data types of key and value. The data type of value is easy. Value corresponds to the answer. Answer is nothing but basically a length of the longest common suffix. So value is integer type. What will be the data type of key? Our key should be uniquely able to represent a pair of I and j. We can use string to achieve this purpose. We can simply add an underscore between I and j. Now this string will always denote a pair of I and j uniquely. So our key's data type can be string. Therefore, now we have the map to solve the problem of overlapping problems. Now let's see how will usage of this map change our algorithm. Now we will have another parameter map of string and integer. So wherever we are calling this method, we will add another parameter map here and here as well. Now in our map, our key will be something like I underscore j. So we will have to build this key using I and j. And now before returning the answer, we will first put the answer in the map so that we can use it for future later. And here, whenever we get an input, we first check in map if we have already seen this input and calculated for it. If we have, then we directly return the result from the map. Now this completes our top-down dynamic programming algorithm. What will be the time complexity of this algorithm? For every pair of I and j, we have calculated the answer once. Therefore, time complexity is order of m into n, where m and n are the lengths of the two strings. Similarly, space complexity will also be order of m into n, because we have stored the results of as many combinations. Let us now see a code walkthrough for the same algorithm that we just discussed. You can also find the link to this code in the description. So in our main function, we take two inputs s1 and s2. Along with the two strings, their lengths n and m are also given. So first of all, we declare a map of string and integer, where we will store the results for a pair of I and j. Then for all I and j, we iterate. We iterate for the values of I equal to 0 till I equal to n, and for j equal to 0 till j equal to m. I and j here denote the first I and first j characters of s1 and s2. For every pair of I and j, we will calculate the length of the longest common suffix using this recursive method. We will get the candidate answer. Now we know that our final answer of length of longest common substring is maximum of all such candidate answers. Therefore, we will have a variable max so far. Its purpose will be to track the maximum length that we have seen so far. So we will initialize it with 0, and if our candidate answer is greater than this value, then we will update max so far. Finally, we will return our max so far. Let us now see how does our recursive method look like. LCS util. It takes as input the two strings I and j that denote the first I characters of s1 and j which denote the first j characters of s2, and it takes another input as map that will store the results for different inputs. So first of all, there is this base condition where we check if I is equal to 0 or j is equal to 0. What does this mean? That means for s1, either we are considering first 0 characters or we are considering first 0 characters for s2. That means either s1 or s2 is empty. In such a case, the length of the longest common suffix will be 0. So we return 0. Next, we need to build a key for our map. To build the key for map, we simply will add underscore between I and j using this method like this. Now once we have built this key, our first aim is to check if we have already seen this input. So we go to the map and we check if we have already seen this key. If we have, then we return our answer directly from the map. If we have not seen this in the map, that means this is a fresh input. And for this, we will have to calculate. So first of all, we check if the last characters are equal. Now since we are considering first I characters of S1 and first j characters of S2, last character will lie at index I-1 and j-1. So first of all, we check if the two last characters are equal. If they are equal, then our subproblem becomes corresponding to I-1 and j-1. So using this recursive method call for I-1 and j-1, we get the answer for our subproblem. And whatever is answer of our subproblem, that plus 1 is our current answer. And if the two characters are not equal, then our current answer is 0. But whatever is our current answer, before returning that, we put that in the map so that we can use it later whenever we encounter the same input. And we return this current answer. So this way, using this method, we return the length of the longest common suffix for I and j. And this completes the code to get the length of the longest common substring between S1 and S2. Let us now see our code in action. So we are giving it one test case. The length of both the strings that we will give to it are 6 and 6. The two strings are ABCDGH and ACDHR. Now let's see what is the answer given by our program. The answer is 4 because CDGH is the longest common substring. So far, we have been focused on returning the length of the longest common substring. There could also be an extension to the problem. The extension could be to return the actual longest common substring and not just its length. How will we do that? Now we already have the length of the longest common substring that we are returning. So if we can somehow figure out the starting or end positions of that substring in any of the two strings S1 or S2, we will know what is the substring we are talking about and we can easily return that. Okay, so we already have the length. Now, if we just simply note down I and j as well, wherever this candidate answer was maximum, at that point, we also note down what was I and j. Then we will very easily have the end position for the required substring in both the strings S1 and S2. Now we have the end position, we have the length, so we can always return the actual substring. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.